Now we can have coupled and uncoupled downgoing slabs. It'll create different stress regimes. A coupled downgoing slab has high compression, creates large to huge accretionary wedges, much stronger earthquakes. This happens when that overriding slab is stuck to that downgoing slab a lot more. So it's not sliding through past it very nicely, it's really stuck against it. So a lot of stress builds up, then it finally releases, and that gives us the larger earthquakes. After it releases, it gets stuck again, the stress starts building up again. And this is, so it's a high compression, large earthquake type subduction zone. Also results in larger accretionary wedges, and the volcanic arc that forms is much more felsic to intermediate, because with all of that compression there are not many cracks open for magma to travel through, so there's a lot more of that succession melting. So by the time it reaches the surface, it's either actually felsic or at best intermediate magma. On the other hand, in an uncoupled subduction zone, that subducting plate can slide much more easily. The overriding plate doesn't keep adhering to it, so the compression is much reduced. The earthquakes are smaller, maybe more frequent, but smaller. That's a good thing for human constructions, buildings and bridges and stuff. And again, it's because the stress doesn't build up for so long before it releases. Also, with lower compression, there are more cracks available for magma to move through, and therefore more mafic magma can actually make it all the way to the surface and come out as more mafic volcanoes, more mafic lava. This is because it rises faster, it incorporates less country rock, it can actually maybe make it all the way to the surface and not have to do the sequential melting, and so the lava and magma are much more mafic. Now, when plates are coming together, there is a collision zone. It's two plates coming together, but if they're both buoyant, neither one can subduct. Or if there's a portion of one that's more as buoyant, that portion can't subduct. Buoyant lithosphere will not go down. It's not like, if you're in a swimming pool and you have a beach ball, you can force it to go underwater. As soon as you let go, of course, it'll pop back up, but you can force it down. There's nothing out there forcing buoyant lithosphere to go down. Gravity is pulling. This is a gravity-driven system, so it will only go down if it's more dense, if it's less buoyant than the mantle material. If it is more buoyant, it will not go down. It will not subduct. Instead, it compresses against the other buoyant material. So this will go on until the driving forces have stopped. The subduction has stopped because the dense stuff that was going down and pulling this buoyant stuff along with it has broken off and headed down to the slab graveyard, and so now the convergence ceases and we have a suture zone. The blocks have now merged. They are one mountain chain. This can happen in a couple of different manners because we have coastlines coming together at different angles and different geometries and shapes and so forth. We can have a zipper-like collision where one part of the coastline has collided and starts creating bulges and mountains. And as the plates move towards each other, the part that's touching will slowly move down, kind of like closing a zipper. We can also have a convergence that's going to be uneven. It's not just going to move from one side to the other, but we have this coastline that's coming towards the other one. So coastline B is dramatically uneven. We have promontories, part of the coast that stick out, and we have recesses, part of the coast that are set back. And so as they reach the other side, locally we might have kind of a zipper closing, but as a whole we're going to have a pretty uneven interface. We'll actually have a small interior sea that forms once these two promontories have both hit. You'll have trapped ocean plate that will slowly subduct, and this recess area will be a saltwater body trapped inland. Also, you note here, because of the shape of the coastline of A, some of it is kind of frontal convergence, hitting it square, straight on, and some of it will be oblique convergence. This part of the coastline and this part of the subduction zone, the way that the ocean plate is subducting, is at an angle. So then as this land moves towards it, because again, we're dealing with curved surfaces even though they're flat when we draw them on paper, is going to be hitting it at an angle instead of straight on. That'll affect what kind of compression happens, what kind of faults we get, how much uplift, how much shearing will that turn into a transform fault. All of this depends on what angle it hits at. So pre-collision, we have an ocean, we have our oceanic plate subducting. Here we have our accretionary prism, we have our bulge, we have our trench, we have our volcanoes forming, our compressional back arc, because in this case our overriding plate is moving faster than the rollback. So this is kind of like the Andes style. But eventually all of this ocean will subduct, and this passive margin material will be running up against this accretionary prism. And that'll start looking like this. This passive margin, this continental rise and continental shelf, get uplifted. As they slam into this accretionary prism, they get flexed and pushed upward. We get faulting due to the stretching and flexing. These turbidites in this trench fill can even get lifted up above sea level. And all this limestone material starts eroding and getting karst action because, remember, this is happening over millions of years. So, this is a snapshot in one moment of time, but it'll be pretty similar to this for millions of years before it gets lifted much higher, before much more compression. This is a slow process. So in the meantime, we're getting erosion and karst formation because of this limestone being exposed. and uplifted. Eventually, many millions of years later, we have a suture zone. So this little bit of oceanic basaltic crust that's trapped right here won't ever subduct. It'll end up stuck and squished between the two different plates. That's this suture, and it's called an ophiolite. It's basaltic deep ocean crust that's been compressed and now lifted up above sea level. We have parts of basement shelf thrust up over sediments, and sediments thrust up over, lots of faulting and lots of metamorphism happening from all of this pressure and heat. This sinking sliver has basically been pulled off, ripped off by gravity, and makes its way down to the slab graveyard at the core mantle boundary. The crust is thickened due to compression. So it's, they got pulled together. B was moving to the left, A was moving to the right. It compressed, the area shortened, so there was uplift, and there was down thrust, in a sense, of the crust. So the crust thickened all, both upward and downward. Lots of faulting, mostly thrust faulting initially. It's not till later that we'll get normal faulting. And here's a slide that I was thinking of quite a while back for that bulge that we get. So we get on the edge of a mountain range, we get a full thrust belt. We've got loading from the mountains forming, and we get this foreland basin. The foreland basin is this little gap. As this thing flexes, we get this gap here, and that's a foreland basin. On the other hand, here, just to the left of the gap, you see there's a bulge. This is the same kind of bulge as much earlier in the lecture. Again, it's due to the flexure of this semi-elastic, semi-rigid material, in this case, the Earth's crust. So here I'm showing it for the foreland basin. That's this gap that forms and fills in, partially at least, with sediment. And then this bulge is that bulge from before. So this is a thrust belt from the accretionary wedges, a thrust belt becoming a basin because of the loading. We also have basins becoming thrust belts. So a basin, like a back arc basin, for example, can then, because of the compression, start becoming a full thrust belt. So it was this kind of extensional basin, start pushing and compressing, everything thrusts upward, and although the ground surface doesn't actually look like this, this is a hypothetical, if there was no erosion, surface. But of course, as this is happening, things are eroding, so we don't have these weird lobes sticking out like this. That's an important thing to note. This kind of drawing is if there was no erosion. This does not show the actual ground surface. We'll see this type of thing again shortly, coming up in another slide.